can start. It's a minute. Well, good morning, everyone. My name is Gerard Graham. I'm here with my colleague Sharif Ali. We will be, I think, happy and privileged to take you through our session on solid Earth this morning. So it's a session that straddles the lunch break. We will have 4 presentations before lunch, then we will have our break and come back afterwards for another 4 sessions. We're going to try and stick to the time as far as possible. So it's about 12 minutes presentation and 3 minutes or so for questions. Let's not get too tempted to eat into the lunchtime, because there's also other things happening during lunch apart from all the nice things that's being served upstairs. So I'm going to hand over to my colleague, Sharif, to introduce the first speaker, and if you have any questions, we'll take that at the end of each of the presentations. Thank you.
Good morning, everyone. So now we are already 3 minutes in, so we will start immediately. So our first presentation about crustal structure of Ethiopian Plateau and the main Ethiopian rift from receiver function analysis. So if Mr. Birhanu Abira Kibret, you can take the floor.
Okay, thank you. My topic of the presentation is crustal structure beneath the Ethiopian Plateau and the Ethiopian Rift. Here are my outline of the topics. First, I will go through background and motivation, data and methods, then result and discussion, and finally I will conclude. So the Ethiopian Plateau and Ethiopian Rift are located in the East African part of the rift system, where the red part on the inset map shows the location of my study. The highland of Ethiopia has an elevation of up to 4,600 meters, whereas rift part is to the depression of -100 meters. With that short distance, the Ethiopian structure is varied from 4,600 meters above sea level to -100. It's huge difference with that shortest distance. And the Ethiopian Rift is characterized by Northwestern Plateau, which is the highest elevation, and the Southeastern Plateau, and in the middle, the Ethiopian Rift, which is divergent plate movement is being happened caused by extension, which is done by magmatic intrusion and a rifting system. While we are studying this area, the Northeast African rift system, mainly will focus on the Afar Depression, the Northwestern Ethiopian Plateau, Central Main Ethiopian Rift Plateau and rift system, whereas the Northwestern and Southeastern Plateau. In this, tectonic stretching were caused by mantle dynamics, magmatic intrusion is being held, as well as rifting system, which is a consequence of tectonic stretching, which is thermal softening, crustal thinning, and all these activities are being held there. Previous studies have been held in this plateau and rift system, and they tried to characterize the crustal structure, mohodeps, and the material underneath the surface. In doing that, the main Ethiopian rift has been estimated to be from 27 to 40 kilometer mohodeps, whereas the eastern and southern plateau have been estimated to from 32 to 48. And heterogeneous mohodeps have been observed in this region. So from previous study, various techniques have been applied. Tomographic study, receiver function analysis, and magnetotelluric and gravity modeling have been studied there. And in these techniques, the mohodeps have been characterized, as well as the partial melting, the plume induced, and magmatic intrusion and plateau uplifting have been studied. So these techniques have been studied, and various analyses have been reached. Further research should be done to characterize this active rift system. This is the area where our study focused. The black inverted triangle is one part of our work, whereas the green inverted triangle is another work. And in the central main Ethiopian rift, where this part of the rift system is the main Ethiopian rift, whereas this part is the Afar. I'm not sure whether it's visible. Whereas the black dot is the seismicity, the earthquake which have been collected for starting from 1906, and it has been downloaded from ISCC AC from UK. So in our study, we have used teleseismic earthquake ranging from 30 degree to 90 degree, and with a magnitude of 6.0. And this teleseismic earthquake have been utilized for inversion of receiver function technique. To the right of this, the P wave coming from the mantle will be inverted to S wave and various reverberations. So the direct pace is the inversion which is happening in the moho. And in order to invert this receiver function, we have used a initial velocity model of AK 135. So to calculate the receiver function, we have used deconvolution technique, and we eliminate the source and path effect, and we rotated the signal to vertical and radial component. And finally, we have applied Gaussian filter technique and Butterworth filter techniques. These are the receiver function that we obtained. The green receiver function is the calculated model, whereas the red receiver function is the synthetic generated model. So in doing this receiver function, we have set the fitness between 77 to 92%. So the 92% is the highest fit of receiver function between observed and calculated, whereas the less fit is 77%, as we have seen here. So the rest receiver function which we calculated is between this range, so we didn't bring it for the sake of modeling here. Finally, this receiver function, by using the computer program of seismology, we have inverted the receiver function to 1D velocity model. In doing this, by using the iteration until best fit of receiver function and its corresponding velocity model is obtained, we iteratively inverted it. When the best fit model is obtained, so the inversion will halt. So this 1D velocity model have been utilized to plot the profile. In the very beginning, we have seen that various profile we have used. So this is the profile which is along the rift, the main Ethiopian rift. As we can see from this plot, the deep blue point over here is the highest velocity result, whereas the yellow and in the middle, the red color is the low velocity model. These three, the upper one is the elevation, whereas the middle is the base inverted, whereas the third one is the VP base ratio. So we try to confirm the base result by VP base ratio. When we compare the middle one with the lower one, the yellow color in the middle is the lowest velocity, which can be interpreted as the partial melt, which has been laid in the mid to lower crust, and this might be due to the rifting process, and the partial melt can assist the rifting process from continental rifting to seafloor spreading, which is commonly believed in the East African rift system. Whereas bean is this the highest elevation, such as Aluto and Tulumoye and Wondogenas. These are the caldera. Under this caldera, low velocity and high VP base ratio have been obtained. So this indicates us beneath this caldera, high partial melt is observed. Likewise, this is a cross rift profile, whereas to the left of this plot, the main Ethiopian rift, and to the right of this plot is the Eastern Plateau. So when we see this profile, to the plateau side, high low amount of heterogeneity is observed. This indicates us the plateau side is homogeneous compared to the rift side. This heterogeneity observed in the Ethiopian rift system indicates us the rifting process is being facilitated by magmatic intrusion and partial melt. This profile is from the Western Plateau to Afar, where the high rifting is being happened. As we can observe, magmatic system is observed in the rift axis. Under the rift axis, high velocity magmatic intrusion is being held. The black dot is earthquake, which is collected from 2000 to 2013. So this earthquake has been observed in the rift axis where active rifting is being held, and this rifting is also facilitated by the magmatic intrusion, which is occurred in the rift axis. So from this we can understand that along the rift axis, high seismicity is observed, and the this seismicity is facilitated by the magmatic intrusion. Whereas this is a similar phenomenon is observed in the main Ethiopian rift, high magmatic intrusion is observed in the rift system, and as well as it's also observed to the western part of the rift system, where a little bit earthquake is observed and the rift is facilitated. So from this we can conclude that using this teleseismic earthquake, we have observed low VS in the upper crust, where sedimentary and volcanic eruption is physically observed, and partial melt in the lower crust is more widespread in the rift system, and fast VS is observed beneath the rift axis. From this we can understand that rifting is facilitated by high magmatic intrusion along the rift system. Thank you.
Thank you so much. Any question? So, Gerhard.
Thank you very much. We can move on to our second presenter this morning. This is on the generation mechanism of the 20-second and 28-second tremors in the Gulf of Guinea from statistical analysis of magnitudes and event intervals. It's Yongyan Chen. Thank you. You can go ahead.
Okay. Good morning, everyone. My name is Yongyan Chen, and I'm from University of Science and Technology of China. And the topic I want to share today is the generation mechanism of the 26-second and 28-second tremors in the Gulf of Guinea from statistical analysis of magnitudes and event intervals. I'll introduce my work following the outlines. As we all know, the Earth is a dynamic planet with abundant vibrating processes like the tsunami, earthquake, volcano eruptions, landslides, and so on. And we can divide the dynamic activities on the Earth into 4 possible types according to their temporal and spatial characteristics. For example, the earthquake events, volcano eruptions, landslide, they currently happen and their source are localized, so we can call them localized and occasional source. And on the contrary, the microseisms, we can see them anywhere and every time, so we can call them ubiquitous and persistent source. And the ubiquitous and occasional source still need to clarified. And the last one is our target, the persistent and localized source. For short, is PL source. They usually have long duration, fixed location, and specific period, but their generation mechanisms are still enigmatic. The PL sources on the Earth are mainly distributed in 3 places: the Gulf of Guinea, the Aso volcano in Japan, and Fiji Island. In 1962, the long period signal of 26 seconds was first detected in the Gulf of Guinea. And in 2006, another 6-second signal was observed in Fiji Island, and it was first thought as a mirror of the 26-second signal in the Gulf of Guinea. But then it was confirmed to be an independent source. And after that, the 8 to 14 second PL source around Aso volcano in Japan was detected. And now there are 3 PL sources in the Gulf of Guinea, and here we are focused on the 26 second and 28 second because they have longer history. And from the map, we can see the 26 second source is close to the coast, and the 28 second source is close to the volcano. Why we study the PL source? There are 2 reasons. First, there are probably similar sources on actual terrestrial bodies, like the Enceladus, the moon of Saturn, Io or Europa, both moons of Jupiter. And so analyzing PL sources on Earth can help explore the internal energy exchange process in other actual terrestrial bodies. The second one, the period of PL sources is close to the ambient noise, so they may cause severe contamination in ambient noise tomography. The PL source usually appear as precursory signals on the cross-correlation waveforms, like the red lines in the figure. So it's necessary to study PL sources to reduce their interference. Previous studies about PL sources are mainly about observation and simulation. Like they study their characteristics, location, and so on, and they use simulation to find their generation mechanisms, but they lack connection between characteristics and generation mechanisms. In 2015, a Japanese researcher used a statistical method to study the amplitude frequency distribution of the PL sources in Japan around the Aso volcano, and he found their amplitude frequency distribution changed from exponential to power law and back to exponential, and it corresponds to the eruption style of Asu volcano changed from phreatic to magmatic and then back to phreatic. So we can find the statistical method effective in studying generation mechanism of PL sources. So we'll use the similar method to study the 26 second correspond to 0.038 Hz and 28 second 0.036 Hz source in the Gulf of Guinea. And by comparing the stations in European and African, we choose the GTAM station in Africa because it has the strongest signal-to-noise ratio and have complete 3 years data coverage. And we analyze data via fast Fourier transform and calculate the power spectral density. So we can see clearly these two signals in the figure A. These two horizontal lines represent these two signals. So we can see they have a specific period and have a long duration. And from figure B, we can see two peaks around the 0.038 and 0.036 Hz. Then we did the magnitude number analysis and time interval number analysis to these two signals. For short is MN analysis and TN analysis. For MN analysis, taking 0.01 as the statistical grade, we counted the accumulative numbers of data for each grade of amplitude. For TN analysis, taking 0.05 as the statistical grade, we count the numbers of tremor events within each grade of interval time. The MN analysis results show almost a linear trend. That means it's similar to the GR relation for tectonic earthquakes. So it means they may be related to some underground structural networks without a characteristic scale. The TN analysis results also show linear trend with negative slope. That means this similar to the Poisson process. So these two sources behave randomly. After that, we discussed the influence factor of these two sources. The first one is swell. We found when the swell shows up, the 26-second source is enhanced for a short time, but the 28-second source does not change. So the 26-second source may be located at a shallower depth, like in the sediment layer, and the 28-second source located at a deeper depth, like in the bedrock. The second one is microseism. We calculate the correlation between microseisms and these two sources, and we found they are mainly modulated by the primary microseism. There are many probable generation mechanisms of 26-second tremor source. The first one, some people think they are related to the volcanic tremor beneath the source Atlantic. However, there are no extant volcanoes around the 26-second source, so it remains to be verified. The second is related to the oceanic waves, but the oceanic waves are weak during period above 20 seconds and have dispersive characteristics, so they cannot excite monochromatic signals like 26-second and 28-second source. Last one, they related to the hydrologic motion, because there are many similar sources on the Earth with the PL source, like the VLP, very low period signal, like the Hawaiian VLP is induced by the resonance caused by the fluid passing through an underground conduit inserted to a reservoir below, and the Asu volcano VLP, the pressure change monitored by resonance in a crack-like conduit embedded within a hydrothermal reservoir. And geology research also shows there are hummock depression structure in the Gulf of Guinea close to the 26-second source. In the left figure, the black square represent the study area and the blue square represent the 26-second source region. And from the right figure, we can see the hummock conduit, the structures. So combine the previous studies and our analysis, we propose the 26-second tremor source consists of a hummock in sediment layer, middle connecting a conduit, and the lower reservoir networks composed of lots of tiny cracks without characteristic scale. And the resonance of fluids passing through the conduit generates monochromatic 26-second signals. And for 28-second, they have the similar structure with the 26-second, but it's deeper. Their reservoir networks is in the bedrock, and probably magma-related fluids passing through the conduit and generate 28-second signals. Okay, that's the summary of this work. We use the MN analysis and TN analysis to study the 26-second and 28-second source in the Gulf of Guinea, and we find the magnitude frequency analysis is similar to the GR relation, and the time interval frequency analysis similar to the Poisson process, and we propose their generation mechanism. Okay, that's all. Thanks for your attention.
Thank you very much. Are there any questions? We have a few minutes. I see a hand at the back.
Thank you for your presentation. I just have a question. How do you localize the region of the tremor source?
I didn't do the location. Some other people did it, so I just used their location. Yes.
And how did they
Localize?
Yeah.
Some people use the beamforming method. Do you know this? They use an array to locate the back azimuth of this place, and so they can find their places, and maybe use some method to locate their distance, so find location.
Okay, thank you.
Thanks for your question.
Thank you. Any further questions? Esan.
Thanks for the presentation. My question is this a unique phenomena or have been observed somewhere else? You just showed us the primary and secondary microseism, which is not a unique. You can see anywhere that by the interaction of the oceanic swells with the ocean bottom. But this 26, 28, you observe only in this area. Is it unique, or you are aware of any other places that have been observed?
You mean the 26-second?
Yeah, similar thing.
Okay. I think they are different because the 26-second signal, they have specific period and can be observed in stations around the world. And when it's in the burst mode, it can be strong as the magnitude 5 earthquake. But the microseism is much weaker, and they have the dispersive characteristics. So I think this phenomenon is unique. Yeah. Okay, thank you.
Thank you for your presentation. Why you call it 26 seconds, just a unique period?
Yes.
Is there no any attenuation with distance? For instance, you showed us time station record date, and there is no any even change in frequency content. Is it consistently observed as 26 seconds everywhere, or that's one thing? And the other one is there a magma reservoir at that location? Maybe it resonates induced by ambient noise or the ocean wave or something. Would that be an explanation for it? Thank you.
Not very. I'm not get your question.
My question, there are two questions.
Okay.
One is why you call it 26 second, because there is no any change in the frequency content of that signal when it travels longer distance. That's the first question, because it is observed at time station, for instance. And my second question is just a remark on the possible explanation. Is there a magma reservoir beneath it? Because of resonance, is it created or what? Just a remark. Thank you.
Okay. The 26 seconds, because they have the appearance is around 26 seconds. Maybe not at the specific 26 seconds, but it's in the frequency band around the 26 seconds. So we just call them 26 seconds, and the appearance is fixed for almost 60 years. After 1962, we found it has existed for until now, and the 28 seconds is same. And because the 26 seconds, there's no extant volcano around it, so we think it's not correspond to the magma. But the 28 seconds is close to the Tom volcano, so we think it's related to the magma. So if maybe we found some volcanoes around the 26 seconds, maybe we will consider the relationship between them. I don't know if I answered your question.
Okay, thank you. If there's further discussion, then I'm sure there's plenty of time still later today.
Okay.
So I'll hand over back to Sharif for the third presenter.
So I just want to say last year we, CTBTO in coordination with Lawrence National Laboratory, organized two RsTT workshops in Oman and Nepal. And it's great to see now one of the outputs from one of the participants in this workshop. So the title of the presentation is Performance of RsttMndc Model in Hangay region, Mongolia, by Sarah.
Okay, hello everyone. My name is Sarantsetseg. Today I will talk about performance of the RsttMndc model in the Hangay region, Mongolia. RsTT is the 3D global velocity model, and RsttMndc is the enhanced velocity model for Mongolia. And today I will talk about the RsTT velocity model, and our purpose is to check the performance of the RsttMndc velocity model. Okay, I will talk about the ILOC location algorithm and data which includes GT events, 1D velocity model and 3D velocity model, also the results, conclusion and references. ILOC location algorithm relocates the events with neighborhood algorithm, which search from the median of reported hypocenter parameters to get an initial hypocenter and then try to find the global minimum. If it's found, the linearized inversion algorithm works to find the final solution. ILOC enables to use 1D velocity local model and regional 3D velocity model and teleseismic AK 135 Earth's velocity model for the same events depending on their distance. Here I will talk about the 1D velocity model for the Hangay region, and within the 2012 and 2014, we conducted an Hangay experiment with the Lehigh University, and during the experiment, we registered 8,233 local events, and to obtain minimum 1D velocity model, I selected the 2,413 events, well-locatable events. Then here is the results of the 1D velocity model, and you can see the P and S velocity models and also corresponding VPBS ratio. The blue line shows the velocity model and VPS ratio independently calculated P only and S only data set, and the red line shows the jointly calculated PS combined result. The crust is characterized by an approximately 24 kilometer thick upper crust that shows a small but constant velocity gradient both in P and in S with an average VPS ratio of about 1.73 for PS combined and 1.75 for P only and S only runs, overlaying a lower crust of nearly constant P and S velocities with a VPS ratio of about 1.70. About the station delays for P and S whole Hangay minimum 1D velocity models, it generally shows a high regional consistency, and they are very similar with the exception of epiperipheral stations and a specific region in the northern Hangay Dome, where 3 stations show late arrivals for P and S phases. Here I will talk about the 3D velocity models. This is the map of Mongolia. The black square shows the study area, Hangay region. And we implemented, we covered, Mongolia is covered by some temporary network, station networks, and the Crustal, here you can see the permanent and temporary stations. The crustal thicknesses is studied by different authors, and in MNDC we use half space model, and we need to change it in the near time. So about RsTT, it's just great. So we need to obtain RsTT for Mongolia. So we made a little bit approach to achieve our goal first, and in order to do it, first collected the obtained crustal thicknesses values under the stations and retrieved the location of the nodes from the RsTT using getNode command, and then interpolated the values under the retrieved nodes are inserted into the RsTT model. For the Conrad thicknesses, we used very old study result, but it is in agreement with the crustal thickness, showing thick crust in the west and thinning into the east. As Hangay Dome is thicker than other parts in the RsTT Mocha figure, and RsTT MNDC Conrad thickness differs from the surrounding area. Now the RsTT model inserted the crustal thicknesses. It is called RsTT MNDC. Here we identified the GT events. There are 205 GT events found. The 35 of them are recorded at the further than 2.5 degrees, which helps to see the RsTT and RsttMndc model effects resulting from the relocation. And the cyan color show the 72 Hangay stations, and the yellow circles show the GT events. Okay, here in the first figure, the GT events and the relocation results are shown. In the first graph, here is the cumulative distribution of distances. I relocated the GT events first with RsTT, then there is 28 events are relocated with it. Then when I relocate it with RsttMndc, there was 32 events relocated. And then to relocate with RsttMndc plus Hangay 1D, all events are relocated, and this is the model that has the highest number of events. To see the graph, the green line, more than 90% of the events located within the 5-kilometer mislocation, and I think the last one is the best model. And here I also tried to show which one is the best one using the number of pages and travel time residual. The first row shows the RsttMndc plus Hangay 1D results, and the middle one RsttMndc, and the last one is the RsTT results showing different pages, how many pages identified with corresponding models. And our crustal thickness is thicker, so the FUPN is good, and also most of the events in the shallow depth, the more crustal pages are good too. Okay, we obtained the 1D velocity model for the Hangay region and created the enhanced 3D RsttMndc model for Mongolia, then identified 205 events in the Hangay region, and 35 of them were recorded further distances more than 2.5 degrees, and tested the location performance of these velocity models, and the epicenters were consistent with each other. It's because of the almost perfect azimuthal coverage. It's very difficult to demonstrate the improvements. The performance of the RsttMndc plus Hangay 1D model was the best among the other models. Here you can see the references, and also I especially thank you for CTBTO having given me a chance to be here, and also thank you for Professor Easton Bonder who helped me to do this. Okay, thank you so much.
Thank you, Sarah. So we can have 1 minute for questions. If we have one question. So no question.
So we also want to encourage those that are online, if they have any questions, to raise that in the chat. I keep looking at it, but it tells me no question. So for you that are online, please let us know if you have a question.
Okay.
Thank you.
Thank you, Sarah.
So our last presentation for this morning, that will take us up to the lunch break then, is machine learning for travel time Emulation. This will be given by Stephen Myers.
Thank you, everybody. And I will start by just saying that a fundamental aspect of CTBT is to collect all of the detections that are made at seismic stations across the network, associate those phases or detections to events, and then use those times, travel times, to locate events. And the more accurately we can compute travel times from any hypothesized point in or on Earth to all of the IMS monitoring stations or other stations, the more accurate that job is. And we start with some fundamental research in developing a three-dimensional Earth model. That's often very basic science. And this talk is about how do you take some of this basic science that does a better job at travel time calculation and make it practical for use in a monitoring network. So this is just the takeaways that I've just described. 3D models predict travel times more accurately than radially symmetric Earth models. They aid in association. If anybody's familiar with the software at the International Data Center, things like GA, Global Associator, or NetVisa, there has been a lot of presentations on that at this meeting, and improve the event location accuracy in codes like iLoc and BaseLoc and any other method. So why wouldn't you just use the 3D model directly? It's because the physics of ray tracing through a model is a little too slow for operational use, even though it's quite fast. It's only 1/10 of a second to a second or so to calculate travel times, but when you multiply that times the number of operations that have to be done, it slows down the system too much. So we've developed this machine learning for travel time emulation, or MALT, to make 3D model calculations more practical for use both in a monitoring system and for researchers who want a snappy travel time calculation. The differences between our MALT travel time emulator and the 3D model itself is small compared to the inherent errors in the model itself and average travel time measurement errors, and I'll be showing some of that later. And the computation time is fast, on the order of 30 microseconds, which is very, very fast, and on the order of just using a 1D model itself. And the last thing I'll say is we just submitted the revised manuscript for this, so this should be out in publication in the Geophysical Journal International, hopefully pretty soon. So this is an example of a 3D model that we've developed, and this is the LLNL G3D series of models. At the bottom of that figure there, you can see the publications that in which this model is developed. It's a series of publications where we did P waves, then S waves, added vertical transverse anisotropy, and included surface wave dispersions as well. Now we're moving on, and we actually have a version of this for computing full waveforms as well. But relevant to this talk is the fact that through this model, we can compute just about any phase that would realistically be used in seismic monitoring. The list of them is there. I won't go down the whole list, but the first one that we look at is just the first arriving P wave, which tends to be the one most commonly used in monitoring and is extremely important for event location. So this just shows some of our previous work on testing the 3D model itself. I'm told that I can get a hand to pop up. This figure here on the left just shows, as a function of distance, the travel time residuals for an average 1D model. That's this black line here. It's very high error in regional distances out to 20 degrees or so, then drops down when the rays are traveling through the lower mantle. With the 3D model, the travel time error that we get relative to a ground truth data set is the red line. You can see it improves things quite a bit at regional distance as well as out to teleseismic distance, and then the dotted line is the percent improvement. When we use this to locate seismic events, this is the center figure here is for P waves, so for travel time paths beyond 2,000 kilometers from the station. We see a average error in the vicinity of just under 10 kilometers for a well-configured network. When we use the 3D model, that goes down to something just above 5 kilometers, and then the percentage improvement is here, so it's on the average of 30 or so percent. For a regional network, the improvement's even better. I note that for regional phases, 0 to 2,000 kilometers, as you add more phases, the location actually gets worse on average because you're adding these picks that have huge biases in the travel time prediction. So you're just adding more and more bias to the solution, and it drives it off of where it should be. When you use the 3D model, you can get this down to sub 5 kilometer, assuming you've got more than about 20 phases. But even if you have fewer, the improvement is still significant. So what we did is where we used our 3D model and trained our machine learning algorithm. This starts with 25,000 plus seismic stations that are in the International Seismic Center database. From that, we selected stations that we think are high priority, like the IMS, and removed other stations that are within a quarter degree of those, just to reduce the number of stations. That process reduces the number of stations down by about half to about 10,000 stations, shown in the lower left there as all of those points on Earth. At each of those, we sampled hypothetical events, and this shows an example for one station in this center figure here, where you can see that there's high sampling density close to the station, as shown in this figure to the right. So that's distance and then sample density. And then as you move away, we have a little less density at regional distance, and then pretty sparse out to teleseismic, where experience tells us the travel time deviations from the 1D model very slowly. So we do this, we end up with hundreds of millions of travel time calculations across the globe, and we then use that as a training for our algorithm. In this case, we have settled on the XGBoost method. We did try deep learning and other things. I presented on that at a previous conference. It works well, but this one is so much simpler, so much faster and robust that we just went with the simplest solution. XGBoost is open source. Anybody can download it. If you took our data set and the parameters that are in our paper, I think that you could reproduce our results pretty easily. It's a very robust method. It trains in about 3 hours on relatively standard a CPU, so that again is an advantage. It's just very simple. And this just shows on the right the general approach for XGBoost, which is an ensemble of decision trees, essentially, where you get one decision tree and then the next one tries to minimize error even further and further and further. There's all kinds of literature on this, so I won't go into the details there, but that's the general approach. So how does it do? This shows at various distance regimes, local out to about 2.5 or 1.5 degrees, regional from 1.5 to 20 degrees, teleseismic from 20 to 90 degrees, and then this is the travel time error, plus or minus. Actually, these are slightly different scales, but that's plus or minus 1 second there, so you can see the vast majority are near zero, but there is a spread around that. And then I've got some statistics down on the bottom that show the MAE is mean absolute error in these different distance ranges. You can see that it's a couple tenths of a second, and then based on our previous studies, the mean absolute error for the 3D model is around 0.6 to 0.7 seconds. So this is a very small error for the machine learning method compared to the error of the model itself. So we tested this against a ground truth data set shown here in the lower left. Those are all the ground truth data points with the different ray paths to various stations. It has decent coverage in the northern hemisphere, some coverage in the southern hemisphere, so it's not entirely even across the globe. But what you see here is the travel time residual, for instance, across this x-axis out to plus or minus 4 seconds, and then this is just the count. The orange curve, or the blue curve, is the residual of the MALT travel time against this ground truth data set. The blue is using the full 3D model, and then the green just shows our estimate of the MALT 3D error. So the important thing here is that the residual distribution is almost exactly the same, regardless if you do the full physics or whether you use the machine learning. And then in the teleseismic distance range, it's similar, where the blue and the orange pretty much overlay one another. So using the machine learning approach doesn't really add anything to the error. One thing I'll note is that it took several hours in this case to compute 3D. It took 1/10 of a second to compute all these travel times for the machine learning. So I'm getting towards the end here, and this just shows that the input is very simple. It's just the event latitude, longitude, depth, the station latitude, longitude, and elevation, and the phase, which right now is only a P wave. You input that into this MALT package. It's about 2 gigabytes, but most of that is the XGBoost code itself. The module that for MALT is only about a few tens of megabytes. In 30 microseconds, you get an output, a travel time. And right now, P phases are the only ones supported, but we're going to extend that, and we can also extend that to path-specific uncertainties. So we're running short on time, but, and I said all of this stuff before, so I just want to read the last thing, which is, what are the next steps? We're going through the process of releasing this code, making it readily available to the general public, and we want to extend it to additional phases. Thank you.
Hello everyone, welcome back to the session 1.2, the solid earth. So this is the second part. The first part we had before lunch, quite interesting talks. So let's start to our first speaker, which is Mr. Rapelang Simon, talking about refined location parameters for the 20 December 2020 earthquake in Gaborone.
Thank you, Chair. Good afternoon, ladies and gentlemen. My name is Rapelang Simon. I'm from the University of Botswana. I will be talking about the refined parameters for the 20 December 2020 event in Gaborone. Gaborone is the capital city of my country, Botswana. Introduction will be the first part. Oh, there's a slight delay. Sorry for that. So introduction is the first part. Botswana seismicity, Gaborone earthquake, data analysis, results, conclusion, acknowledgements, and references. For those who do not know where Botswana is, because we have to place the context, it's a landlocked country which is surrounded by Namibia to the west, south is South Africa, to the east is Zimbabwe, to the north is Zambia. I will not bore you with geology, but what I would want you to pay attention to is this region here. That's where this earthquake took place, close to where my pointer is there. This is a stable area. It's part of the Craton. That's the Cape Craton, for those who have heard of the Cape Craton. There was a big experiment which covered the southern Africa, and some stations were along in this region. So the experiment itself was called the Cape Craton experiment. In terms of seismicity, Botswana is really not a very seismic country. It's starting from independence. Botswana's independence was in 1966. The seismicity was dominated by events which are in the north, which are indicated by these red clusters there. That's where the Okavango Delta is. And there are several faults in that area, and others think that is an extension of the East African Rift System. So most of the events or historical events are in that region. So historically, seismicity has been in the Okavango, and of recent, that's when now we start seeing events down in central Botswana and almost everywhere. Again, there are other factors in play, as Botswana is a mining country, and all this play into this. So seismicity really is dominated by events of low to moderate magnitude. So this Gaborone earthquake occurred at midday on Sunday, 20th December 2020, and was widely felt across Gaborone and the surrounding areas of villages. And according to Kwadiba et al., the perceived ground shaking ranged from weak to strong shaking. They estimated that the modified Mercalli intensity scale values were in the range 2 to 5. So most of the people were still in church, and others were still driving from church. So some of us, we didn't feel it because of that situation. But eyewitnesses whom I got to talk to, more especially those who were at the dam, they indicated that they saw water like it was boiling, obviously indicating that there was a projection of water into the air at the Gaborone Dam, because it was right in the city. However, the level of the water in the dam didn't go down or whatever. It was not affected really. So this event did not result in any deaths. There were no casualties. There were no damages to property. But those who were in their resting after church, they indicated that their beds were shaking and they were wondering what is happening. In terms of how we got to record this event, we have local stations that recorded this event. These are part of what is known as the BSN in Botswana, which is Botswana Seismic Network. So 8 of these stations, which are in the southern part of the country, this pointer is, I'm used to a nice pointer, not such a difficult. So the southern parts, that's where we see LBTB. That's the station which is sending data to CTBTO. It's an auxiliary station. So those were the stations which recorded this event. In terms of the coordinates, here we show all the stations which we used for this data. We had 13 stations, meaning 8 local, 1 IMS within Botswana, then 4 outside Botswana, which are from the region, 2 from South Africa, BOSA and SUR, and 1 from Zimbabwe, MATP, and 2 from Namibia. The waveforms of the Gaborone event were analyzed using GeoTool software, and this is a software which is provided to NDCs. So the intention, as you know, here at CTBTO, the important thing is to really have good location so that in the event of someone, let's say, detonating a nuclear or whatever, then one should be able to locate that event as best as possible. So the intention was to get origin time, epicenter, and the focal depth and the magnitude using GEO2. So the waveforms used in the analysis were from 13 broadband stations. The nearest or closest station to this event was at an epicentral distance of 0.43 degrees. Only unfiltered components with clear faces were used for this analysis. So we had 13 P faces from vertical components, then 4 which were clear from horizontal components. In terms of the local model which we used one, we modified one of our old model, this model written Wright et al. This was for the Craton. It's a model which we came up with for the Craton, which goes up to 320 kilometers for Southern Africa. So we modified this model. So the GEO2 analysis was followed by analyzing the event using the regional seismic travel time model, the RsTT. For those who were here in the previous talk, you would have heard Myers talking, is the one who really was of assistance with this model. And Bonda was also here. So it was used to obtain the origin time, the epicenter and the focal depth. So RsTT was developed in the USA at the Lawrence Livermore, Los Alamos, and Sandia National Laboratories. So these 3 labs were very important in doing this model. So this RsTT is used to improve the accuracy of regional seismic travel time and the event location. So RsTT computes the travel time using vertical cross-section of 3D model between source and receiver. And the RsTT model uses nodes closest to the station, location. So if there are 2, let's say there's one node here, another node, it will use both nodes. So these nodes are just 1D velocity, more like 1D velocity model. Hence, the travel time calculation for a given ray can be used several nodes, depending on the location of the station. So for local distances, a 1D model at the station is used to compute the travel times. The 1D model is a linear interpolation of layer depths and layer velocities from the nearest model nodes. RsTT requires initial hypocenter information in the form of a bulletin. So in our case, the parameters of the Gaborone event from GEO2 or results from GEO2 is what we used as the initial hypocenter information for RsTT. In terms of results from GEO2, the epicenter location was at 24.701 degrees south and 25.930 degrees east. Origin time was 10:44:46.6 UTC. Local time there, they say typo is supposed to be plus 2 hours GMT. So it's 12:44:46.6. Then their certainty is plus minus 1.98 seconds. The body magnitude, MB, 4.2, plus or minus 0.2. Local magnitude, 3.6, plus minus 0.5. Depth, 11.3 kilometers. In terms of RsTT, the epicenter location was at 24.710 degrees south and 26.032 degrees east. The origin time was 10:44:46.787. which is a local time of 12:44:46.787. So the depth was at 10.6 kilometers. Why this event is of interest? This is an event which is right in the city and at a critical infrastructure. As you see, I don't know how clear it is. I wish my pointer was the one which points at, was the one which I use for pointing that side. But it's closer to the dam there, so how I went, I can't remember. So the green, the way there's a red place marker there is the Gaborone Dam. That's what the dam which supplies the water to this whole city. So the geotool results show us that the event was very close to the dam. The RsTT results show us that the event was a little bit around 10 kilometers away from the dam. But this is right within the city. So that's why it's really of interest to us. So this Gaborone earthquake occurred in the upper crust. We infer this from what? From the project of the Caval Crichton. Then someone worked on the crustal thicknesses. They got the closest station to Gaborone is SA62. So, and it gave a crustal thickness of 40.5. So which places this event in the upper crust. So, and they used the data from the Caval Crichton project, which is normally called the Southern African Seismic Experiment. So what we see again here is important to have a station close to Gaborone city, because so that we can have control of these events in terms of their depth. And we see that the IMS data and IDC products are useful in civil and scientific applications. RsTT results, they agree very well with those of GEO2. Thank you.
Thank you for the talk. We have time for one probably quick question. Yeah, please.
If no one else has a question. So I have a question.
Yes,
so just one probably more of interest. Did you maybe do a macroseismic survey or something to actually determine, maybe get more of a ground truth into where the event actually was, to also see how accurate your geotool location was?
We tried, but we had a slight hindrance because closer to the dam there is a private property. And I went there 4 or 5 times to try to gain access. So, but it was difficult. But otherwise, the other areas we moved around nicely. There is nothing, you see the geology in the area such that they say granite, Gaborone granite, you might know, Michelle. So there are no expressions on the ground, nothing. So closer to that private property, that's where from a distance one could see that there was also some material which has been being moved. Probably they sell them some quarry also. So whether they could have ignited that or induced it, we don't know. Thank you.
Okay, thank you. So I can hand it over to my colleague Michelle for the next talk.
Thank you very much, and good afternoon, everyone. So our next talk is, thank you very much. Thank you. So our next talk is entitled Deep Learning and Template Matching Detectors Methodology to Seek for Seismic Clusters in the Central Andes within the Bolivian Orocline. And this is done, presented by Gonzalo Antonio Fernandez. The floor is yours.
Good afternoon, distinguished Polish. Thank you very much for the conference, and congratulations to all the logistics that you have made possible to come many people here. So in this presentation, I would like to show our latest research as a national data center. which was titled as mentioned before. So let me talk about agenda. Here we have the tectonic background, we have the matching filter procedures, the artificial intelligence, IMS data, and temporary seismic experiment, which is very interesting because we have already joined 2 NDCs, which is within the treaty of the protocol. Let me introduce my country. This is my country. As you can see in the right figure, you can see the subduction procedure, which is between the Nazca plate and the South American plate. Within this context, we know that we have the different geological morphotectonic zones, which are showing different colors. So we can show you in the on your left part of the image, you can see the altiplano, the Western Cordillera, the Altiplano, the Eastern Cordillera, Interandes, and the Subandes. Also, we include the Chaco and Beni basins. In this part of the structure, you can see that all the earthquakes are dominated by the subduction process. So maybe you can ask, but Bolivia is not so seismic active like Chile or Peru. Nevertheless, I would like to show you that yes, we do have seismicity. For example, we have the shallow earthquakes that has a depth from 0 to 75. We have the intermediate earthquakes from 100 to 350 kilometers, and deep earthquakes from 500 to 700 kilometers. As you can see in different colors, in yellow, orange, and red, are distributed along the country. So you can see also that we have historical earthquakes that have destroyed our countries. I talk about magnitudes above 4. Within this context, I would like to show you how we are start to be involved with the CTBTO. My country signed it and ratified the treaty, so they designated a permanent mission. Once the permanent mission was designated by a law or Supreme Decree, they nominated the Observatorio San Calixto, a non-profit institution, like the National Data Center. And why did they do like this? Because we have 110 years old of experience doing that. In that sense, we also have already worked with the French Corporation and the AFTA Corporation. The objective of this cooperation within the framework of the CTBTO is to have the seismic and infrasound monitoring, research oriented to hazards, and knowledge spread into the society. Saying that, I would like to show you that suddenly we started to record more earthquakes in the central part of Bolivia. Here, for example, I show you the Bolivian Orocline, which is the central part of Bolivia. Sorry for repeating that. And it's the region where we have a lot of shallow earthquakes. One of the latest earthquakes that destroyed Iquiles city was in 1998. And also we have some historical earthquakes like 1909 in Sipe. Nowadays there are 2 million people living in the Bolivian Orocline. So you can see that the seismic hazard is higher in that region. Saying that, we started like let's say like a hobby. We took some 24 hours from a primary seismic station, El Paz station, which is located in the western part of Bolivia. And we started to compute and to extract some templates. The idea was to detect and to optimize some of the daily routine. We also, as we don't have a lot of seismic stations, we also took a normal seismic station, let's say a medium broadband, and also started to select some templates. In this case, I call it SOET seismic station and El Paz. We noted that both templates or both waveforms had a very good signal to noise radio. So we started just to shift these templates to detect and to help the analyst procedure. Saying that, we started also to use the cross-correlation or match filtering detection. We put the same template to different waveforms, but of course in the same station, and we started to record, to detect, and we obtained at least 73% of correlation, as you can see in the El Paz station, the primary seismic station. This is good because it's a, it's a high-quality seismic station. However, and furthermore, we also apply this technique to some local station like SOT, which is located in the center, and we also could find a good correlation, like 82% of correlation. However, the waveform are a little bit shifted. This can be corrected by the analyst. But within this framework, we started to find some families, and we were enthusiastic to also detect some templates with an auxiliary station. That's why here we started to construct a database with only 3 stations. With these only 3 stations, we started to make some threshold limitations, and we define it not empirically, but with at least with 1,065 earthquakes, that we can use a 0.7 threshold level to detect and to validate an earthquake. But of course, they are only 3 stations, so you made the seismology community will know with only 3 stations you can have a lot of error, and your ellipses of error will be like huge. So in that sense, we found some families. That's why we started to ask ourselves, will the filter matching work as a detector? Will be good to work with that? Will help us to enhance the epicenter? Then we have another question. Most of the stations, as you can see here, are far away from the central part of Bolivia. So we noted that there are some path effect in the templates, and not always you can detect at least 10 earthquakes for one family. Then we started to think it will be useful to detect lower or moderate magnitudes. We'll be able to have just 3 or spare network to keep tracking or to keep detecting some seismic stations, earthquakes, sorry. In that sense, we started to read the artificial intelligence. You may know that there are a lot of articles. They started to like tools for detections or models like the SnT models that they are ready, let's say, plug and play to start detecting some earthquakes. Will help us? We don't know. We will try. In that sense, once we found some families in the central part, we started to train, to retrain the SnT model, like not like a hobby, but I can say like the first steps with an open source software called Quake Library. We took all the data possible that we have registered, historical, and also some data which is using recently. We used the IMS station. We succeeded in the first step to train this small database, which is small in our cases, and we started to do and run the filter match detections. So we enhanced this database, we obtained more templates. As you can see in this figure, we started to detect these earthquakes, and then we pick by hand our phases. Once of that, we are, then what can we do with this information? Then we were a little bit, with a little bit hope. So we wanted to apply the Derot, in the last paper of Derot, Benoit Derot research, we applied its workflow. So it's related to more or less, no, it's already related to a deep neural networking detector, where you can set up a threshold for the P and S, and also an advantage of this is that you can make some association, which means that you can pay like in a real-time association and location based on a simple 1D velocity model. For example, a result of that is you can see a main shock, but then you can see a lot of aftershocks that were detected and located within a simple and dispersed seismic network. Saying that, we attract the attention from the French NDC, because it's for the first time that we started to locate the accuracy and not a lot of problems in the resolution of depth. So that's why with the French NDC, we have a project right now that we installed 11 seismic stations, 5 broadband and 6 short periods in the central part of Bolivia. And you can see in the other, well, the green triangles are the broadbands and the blue triangles are the short periods. As these both NDCs are working together in this project that will last until 24, we have started to recover and to analyze by hand and automatically the events. So that's why we have this these cumulative graphs. The orange triangles represent the automatic detections, and the blue triangles represent the manual detections. You may note that with the orange triangles, we have a magnitude of completitude less than 1. Which is very positive because we corroborate and we can confirm that we can have low magnitude earthquakes within this region, which is very important. So in this graphic, I would like to show you 3 different histograms. Once we have the detections made by hand and also automatically, we coordinated with the Benoit Derot, the work to compute the difference between the manual and the automatic P phase, S phase, and also the origin times. You can see that in the 3 histograms, there are not so big difference. But more interesting is that we have, with only 8 months of data, you can see in gray lines, if it's possible to see, we detected a swarm of earthquakes located at the Chapare region at the eastern part of the Bolivian Orocline. Then we detected a lot of small earthquakes with magnitude 0.5 to 1.3, like a swarm in CTBTO. You remember that I talked about CTBTO 909 earthquake, which destroyed the city. So it has started to happen something. There's something that is happening, as you may see. In that sense, we plotted that the same data. We thought initially that in the red dashed line was the main reason to activate the shallow earthquakes. However, you can see in the eastern part, lower left in your figure, that there are some cluster earthquakes with low magnitude, and it's called CTBTO. Then in the western part, you will see that a red star, which is the Chapare earthquake. With this information, we noted that in the both sides of the Bolivian Orocline, you can see that the earthquakes are happening. It's low magnitude, true, but they are possible to detect and they are possible to analyze within this small seismic network, temporary seismic network. In this slide, which is this crosscut section comes from Spark 219. So he made a graph of the geological part of Bolivia, a crosscut section, and we started to note that there are 2 clusters, and they're well constrained, and the depth is also well constrained. So in that sense, we validated the procedure that was presented before. Not a conclusion, but yes, a discussion. We started to build a template to find more earthquakes, to try to discover more families, and to try to create catalogs for further studies. Furthermore, we noted that the interferential intelligence or with data that comes from IMS or other machine learning procedure or deep learning procedures can help us to reach magnitudes of completitude of 0.8 local magnitude. And then we noted that there are some softwares, open softwares that you can use, you can set up like Real or Seismic to do the location association. And if you have a temporary seismic network dense like this, then you can start to enhance the depth, the constraints of depth. Our next step will be to use HypoDD for those seismic clusters. We know that there are a few earthquakes, let's say a few, but will help us, nonlinear log or other procedures. So this is the team. As you can see, we're at the National Data Center, and this is all the team that we work at the Observatory in La Paz, Bolivia. So thank you very much for listening to my presentation, and I'm glad if you have some questions. Thank you.
Thank you. Thank you very much for that. I'd like to open the floor for some questions. We've still got a bit of time. Any questions? I see there was one. Do you want to perhaps read it out?
Yeah, there is an online question. How do you label intermediate or deep earthquakes? I guess it's between 350 kilometers and 500 kilometers, if there are any.
We used a simple method. We used like 100 years catalog. Then we divided that earthquakes, and we can see the difference between the P and S. Then we use IPO 71 to constrain the depth. And that's why we have a, sometimes it's tricky. Some authors call like only deep earthquakes if you go beyond 100 kilometers. However, for Bolivia, it's very interesting because we have in this range 100, and then you can have 200 or 305 kilometers. So we are based in this catalog. We consider them like intermediate earthquakes, but as the earthquake of 1994 happened within the 500 kilometers, we started to have a small group of deep earthquakes. So we validate that using the HyPO 71, reading the international bulletins like ARB or CEL3 or the IS bulletin. So that's why we corroborate that in Bolivia you can have these shallow earthquakes, which is not well constrained, that's true, but we're starting to enhance that. And the intermediate earthquakes that we preserve like intermediate, we prefer to preserve like intermediate, and then the deep earthquakes. So we validate like HyPO 71 by ourselves, but then use international bulletins also.
Thank you. Thank you very much. I'll now hand the chair over to back to you.
Before that, I just would like to mention that we receive online questions, so if there is any, we can, I assure you to ask your question to the speaker. So the next talk is estimation of mantle transition zone seismic discontinuity beneath Northwestern South America from peer receiver function analysis, given by Professor Carlos Alberto Vargas.
Good afternoon. This presentation was scheduled originally to my student. Jorge is not here. He has solving some issues, familiar issues, so we are facing now this commitment. Okay. Let me start with this line, just a couple of minutes explaining about the techniques, because normally in these scenarios, the people are not homogeneous in concepts. The first issue to bring is why we need to determine, to estimate this contrast of impedance in the mantle. What are important in seismology? Well, basically, those are fundamental studies for understanding the tectonic plates, are also important in order to explain the orogenic systems, and also for the mineralogical studies, or for understanding the stabilization in surface. In this case, you can see a couple of, in the left side, a couple of changes on velocity that more or less are related with these discontinuities, 410 and 660 kilometers depth. In the right side, you see the equivalent. Now I'm going to explain how are explained, what are the hypotheses behind this contrast. You see the mineral composition in the shallow part is almost near to the oceanic cross. It's about 100% of olivine. Once we are moving down, there are transformations. The first transformation is from olivine, in this case is alpha, to olivine beta. That is this mineral that you see in this contrast between 410 and 520 kilometers. Then from Rikswoundheid, that is near to 660 kilometers. This is olivine alpha, beta, and gamma. And then we are going to have, after 660 kilometers, the mineral perovskite. Basically, this is the contrast of density that produce these changes of velocity. For almost 1 century, we have seen anomalies in the seismograms. We have tried, at least in the five decades, to explain in the seismograms what translate these signatures. Well, one of these techniques is the receiver function technique. The technique basically is trying to obtain the most vertical signal in order to estimate times between this contrast of impedance. In the middle of this slide, you can see how strong are some of these contrast of density. The first, the blue color, it corresponds to the cross. The second, red anomaly, corresponds to the lithosphere-astenosphere boundary. And you see later one small weak blue color anomaly in 410. Once again, weak in 660 kilometers depth. Many studies have been done previously. In the previous Here in this, in the right side, you see several maps. In 1998, for example, there are reported global distribution of these anomalies, and later in 2005 and 2008. And many other studies have been done after this work. Well, let me check a little about the tectonic setting of the area. We have an area where are converging 4 plates, South American, Cocos Plate, Nazca Plate, and Caribbean. It's a converging margin. Seismicity here is very intense. We have several seismic nests with different depths. Of course, we have a very populated region with these earthquakes. Well, this is a topic of high interest. Well, look, what is not really of interest is trying to explain these anomalies in depth. Well, in this area, we have about, at least for this study, 98 stations. 4 of them, one located in Ecuador, another one in Colombia, other one in Venezuela, and the last one in Panama. With these stations, we have incorporated a catalog of about 2,000 teleseismic events recorded in these stations. The magnitude of the events, they should be very far, between 3,000 kilometers to 13,000 kilometers. We need basically huge, large energy. Earthquakes used here ranging between 4.7 and 8.1 of magnitude. In total, we estimate 66,000 of receiver functions. Of those receiver functions, we selected 50,000. This 15,000 high quality was used to estimate the morphology of those discontinuities. Important is that the record has incorporated about 30 years of the records. Some stations are very well. You see, for example, previous to 1993, other ones like the Colombia in the Rosal correspond more or less 20 years. So in total, we have a very good record for made estimations. Once again, here, part of the concept, we have the first peak is a approach for the crustal thickness, the second, the third. The third, for example, is the lithosphere-asthenosphere boundary. You see the last two, very small spikes that corresponds to those anomalies that we need to explain. Well, the rays not always come in vertical, so we need to migrate, try to make to estimate how are the most vertical scenario. And throughout this process, we have the chance also to estimate the piercing point, when exactly or where exactly are just crossing these discontinuities. Here we have one example also. In the process, we need to rotate in order to improve the signal-noise ratio. Like example, in the left side, you see one typical seismogram in 3 components. Once rotated, you see how well is the ratio of signal noise. Once we have this process, well, now we are going to detect along the time and then traduce it into the depth and try to find the points or the pierce points. In this map, you can see all those points where are crossing both surfaces. In this study, we selected areas about 100 kilometers of radio in order to incorporate all these piercing points. And then with all this signals, we stack it and average the information about the place. Here you see in the left side one map of the distribution of the frequency of the points where we have more information. The areas outside are less dense information. In the right side you see the diverse piercing points since different source global-wide. Here you see in the left side again the typical receiver function seismograms. You see the spikes for both anomalies, and on the right side you see one comparison between both. If we have an homogeneous median, probably you have a line, but in this case, this figure say that we have a very heterogeneous median. It's not true. Discontinuities has 410 kilometers, and sometimes it's shallower, other moments are deeper. The map on the left corresponds to the map of the discontinuity of the 410, but you see the range between 380 and 440 kilometers. And the other one is also with a broad range of depths. Several authors have used the estimation of both in order to explain the presence of some anomalies. Let me explain again about the scenario. This is the corner of South America. In the right side, we have Craton region and one transition region linked with continental and also oceanic rocks. Mesozoic, basically all these color polygons, and the right side near to Brazil, Venezuela, correspond to very old Plateaus. On the right side, you see also some limits of this orogenic system that are basically bordering with faults that may explain some behavior of the distribution of these anomalies. What you see on the right side is basically the morphology that we found in this case. You see, for example, in the left side that we have one morphology of the thickness of 250 kilometers. Remember, 250 is the difference between both discontinuities. That is less than 250. Well, in several papers previously published have been postulated that it corresponds to zones where there are mantle plumes. Well, for first time in this region, we have tried to follow how are these anomalies. We are reporting in this case the presence of one mantelic plume in the northeast end of the Nazca plate. Probably is connected with the Galapagos, maybe. Yes, it was part of the discussion. When Farallon plate broken, maybe part of this anomaly come to this part. In several previous studies, tomography studies, we have reported in the last 5 years. We have also mentioned the thermal anomalies just in this area south of Panama, western of Colombia. In the other areas, in blue color, correspond basically to areas where we have a very thick layer, probably very old, very cold regions. I'm not going to read these conclusions, but this is my chance to say that thanks to open data sets, we have the chance to do open science. I think this is the a very important moment when if we promote to open data sets, we are going to have more social justice in terms of the scientific evolution, the good education. So this CTBTO data set, and also for Colombian institutions, we are very happy, very proud that my country have opened all data sets. This is a message for other countries. Please open data sets. We have good contribution. There are many people that are working with this information. Oh, well, that's all. Thank you so much.
Thank you for the talk. So you might have time for questions. Yeah, please. Please wait for the microphone.
I was a little bit late and I apologize. So maybe you already mentioned it, and I am asking a silly question, but do you see in your receiver functions any sign of the top of the slab? Because you're using earthquakes within the subducting slabs, and you stress the upper part, but do you see a little bit of the plate-to-plate transition?
Well, it's a very good question. Thanks for it. Let me remember you just at south of Colombia, north of Ecuador, we are detecting a very cold area, that we are linked with one anomaly probably. We change of the angle of the subduction of the Nazca plate in this sector. It's very, very clear for us in this area. Other previous studies in Venezuela last year, it was published for other team, reported very steep angle of subduction, but just in these interfaces changing completely. So in some way we have detected these changes. This is the last one, I think. Okay, is here. You see just in this area, blue near to Ecuador, corresponds to all those earthquakes area, very depth, 600, 500 kilometer depth. The deeper earthquakes of South America, well, similar like Bolivia. Okay, thank you so much.
Thanks again. Okay, yeah. One more quick.
Okay, anyway, you are
there's one
coming
more question.
already this side. No, thank you so much for your presentation. Just on the 660 discontinuity, how clear is it? I was expecting that with slabs diving down there being cool, it should not be so strong. Also, the 520 discontinuity, I'm not so convinced looking at what you showed there because it doesn't come out clearly. What's your thought on that? 520 discontinuity. Thank you.
The place that can penetrate these discontinuities probably decompose completely. Part of this decomposition is a mineral dehydration process using 660 kilometers depth. Part is just moving down, but the other part is coming up like a process of convection. It responds to you or it responds to you? Okay, thank you so much.
Okay, thank you.
Thank you very much. So I'd like to introduce the next speaker and the last talk for the afternoon. And the title of the talk is a seismogeodetic network in southern Mexico to monitor crustal deformation in real time. And this is Gerardo Suarez. The floor is yours.
Thank you very much, Michelle. Yes, it's seismogeodetic. You're absolutely right. Well,
this one is no. This is there a pointer? It shows or not? Okay. Well, thank you. Thank you all for being here, and Michelle, and conveners, thank you for inviting me to present here. A seismogeodetic network is precisely the combination of a seismic instrument and a geodetic instrument, a GNSS receiver. And it's not such a novel issue. It's being done in many places, but I think the seismogeodetic network in this part of Mexico is unique in the sense that it's a homogeneous network, and it's in a region where we expect that we can have some interesting results. In terms of the roadmap, what I would like to show you is more or less what is it, how does it work, how is it composed, what is the advantage that we have from using seismic and geodetic instruments together. Secondly, show you some of the products we have. The goal of the network, as I will show, was to monitor a seismic gap. With all the ifs and buts that seismic gaps have, we have a region in Mexico which has not had a major earthquake in the subduction zone for the last 100 and some years. So there is concern, because it is the closest point in the subduction zone to Mexico City, that it will create very large acceleration. So the reason to monitor was that. And finally, show you some of the short-term and long-term products that we're beginning to get. I won't talk too much about the science because it's slowly and gradually coming up. The location of the network, you can see in the small inset, is in south central Mexico, and it's the oval. Unfortunately, I don't have a pointer, but the oval that you see there, the purple-colored oval, is more or less the location of the gap. And of course, gap is a very qualitative statement that it's simply the region where we believe there is a high probability of a large earthquake occurring. So the funding agency that has given the money for this insisted that we put it there to monitor long-term the crustal deformation to see if we could see anything, and of course the seismicity. If you look at the figure on the left, it is essentially the same figure that I showed before, but I show an extension. I show an extension, those red arrows, because we don't know where the seismic gap will end. And I don't want to go too much into that, but it's been also many, many years in the southern part of the main gap where we have not had earthquakes, so there will be probably more. And on the right, you see those dots. I can't see whether they're triangles or whatever, but you can see those symbols that represent the location of the stations. And we extended well beyond that perceived gap in order to be able to monitor it. Now, what is the seismogeodetic instrument? Well, it is an instrument that has, as I said before, a very high quality GNSS recorder and a force balance accelerometer. The combination of the two gives you an advantage that you can use the high quality accelerometer data to continuously monitor the GNSS result, and with a filter that's called the Kalman filter, which is a predictive filter that is very often used in telecommunications. Once you see the difference between the two, you can use it. It's a recursive filter. You can use it in the future, and then you calculate again, you continue to use it. So the result is then that you have three data streams. You have one strong motion, just regular strong motion data, sample 200 samples a second. You have a high quality, and I will show you some results, surface deformation data that we believe we have accomplished about plus or minus 2 millimeters, a little bit more in the vertical, using this Kalman filter plus the real-time dynamic correction that is provided by the manufacturer. And finally, we also get, because it's always useful, the raw data. Those of you who work in GPS and GNSS, it's always good to have the raw data so you can post-process. So we have the three products that we can compare. And I will show you some results of that comparison. We have tried to keep, by force, the strongest force is the budget, because our budget is limited and a lot of it went into the instrumentation. We have tried to keep the infrastructure at the stations as low cost as possible. And here you see an example of some of the stations. That pillar that you see there, which is unusual for a seismic station, is where we normally place the GPS antenna. It's a very solid. We've looked at the vibration, and it vibrates very, very little. It doesn't really affect the geodetic data. And we build it in a very robust manner because most of these places, as you could see from the map, are along the coast. And unfortunately, the coast of Mexico, for historical reasons, is not very densely populated. There are pockets of very high density of population, like cities, touristic cities like Acapulco or Ixtapas, Iguatanejo. But in general, the population is very low. Plus, the infrastructure is infamous, really, because there are so very few people. Internet is practically non-existent. Some schools have it, but it's very irregular. And cell phone communications is also very unstable. So this was one of the things that really helped us in the beginning, is the little antenna that you see with a green circle. If you guys can see it from the back. It's the size of a switch, like you have in your office or an office modem. But it's a satellite modem that communicates in L-band to a Mexican national security satellite. And it took us a good 3.5 years to convince them to be able to use them. But it's fantastic because the power consumption, as you see here, and I don't work for Hughes, I work for the university, but the power consumption is fantastic. It's 10 watts on average. We've been measuring it continuously, which opposed to what the Seismological Service of Mexico uses, which is KU band communication, which is roughly 50 to 70 watts, depending on how you transmit. It's an enormous advantage because we can keep, as I said before, our infrastructure very, very simple, very sturdy, and very resilient to the region. So this was really the game changer. And the data availability, and I'm copying what I learned here, we're estimating timely data availability, and data availability is really very good because it has practically no outages. It's a dedicated satellite, and we're one of the few people actually using this particular band, so that helps. Let me then show you some of the data finally. So this is all the installation process. What I'm showing on the left, which is the base of the arrows, if you wish, is the location of the stations that I'm showing. One station in the northern part of the array in the top, and a station in the central part of the array at the bottom. And what you see two different types of symbols. The red symbols are the real-time daily averages. So I will show you some real-time data, but these are the daily averages that we compute on a daily basis based on the real-time data that we get. And the red ones are the post-processed data. We have a colleague that is one of my co-authors. It didn't show. I would like to show the initial page, which has the names of my colleagues and students. But she's a colleague at the Institute, and she post-processes the data. And as you know, post-processed GPS data, that includes the satellite orbit changes and atmospheric changes and electron content changes in the upper atmosphere, is much more precise. And we were very happy, and we were actually surprised that if you compare the two, and you can't see the lines, but each horizontal line is 2 centimeters. That's why I mentioned at the beginning that even in the horizontal, in the vertical, which is the upper quadrant in each one of these two figures, of course, the quality is less than in the horizontals, but we follow very, very closely the averages, the daily averages that we get from the post-processed data, from this and other nearby stations, and we get them at least 2 or 3 weeks later once the satellite orbits come in and we can begin the processing. So This gives us confidence that on a daily basis, we can monitor the deformation of the coastline, the deformation of the subduction zone in a continuous manner. And one of my students is working on some machine learning process to be able to monitor changes and report them. The other issue, well, that is simply the conclusion that we can actually do, we actually do have very high quality deformation data at this level of accuracy with which we can monitor the subduction zone, a good portion of the subduction zone. Now, the other issue, of course, is the real time. Our sponsor was very interested in having real-time response of potentially very large earthquakes in Mexico. They wanted to know the magnitude. The seismological service, as everyone else, has trouble with very large earthquakes in determining the magnitude, even though they're using very novel techniques and they've done it very ably using W phase and so on. But you have to wait until the waves develop, and you have to give it a little bit of time. And also they were interested, even though we're not responsible and will not be responsible, of the tsunami warning capability if we can monitor the deformation of the coast in real time. So that was the second test we made. And when I'm talking about test, it's really because I didn't mention it, but the funding was given to us just prior to the pandemics. So installation has been a tremendous challenge. And here we are, although there's a lot of work being done in the other sense. But this is the real-time response. We were lucky enough that as we were beginning the installation in 2021, there was an earthquake in Mexico, precisely in the region where the first two stations were put in. In the upper part, you see some yellow dots. That is the location of we think it's a good relocation of the aftershocks of that particular. It's a magnitude 7.0. It's nothing great compared to other subductions or to previous earthquakes. But if in Acapulco, the station, the earthquake occurred just offshore the city of Acapulco. To the right-hand side, you see the deformation. It's not the seismogram, if you wish, the deformation seismogram in real time. You see the origin time and the arrival of the S wave, and then you see the deformation of the ground and the permanent post-seismic deformation of the coast, which was about 25 centimeters. And again, we could determine that in real time, which coincides very well with the later INSAR studies that we have seen. So we could also answer this question that yes, we can actually monitor real-time crustal deformation. This is the vertical, but we could also do it on the horizontals. And with that, I won't go into much detail, but we developed an algorithm inverting the results of these deformation. I'm going to finish, but I was thrown up by the buzzer. Of using the deformation of the coast in real time, we have this inversion program that can actually, based on what we observe in different stations, in about 3 minutes, we can have the magnitude, we can have the actual deformation, and we could warn the Navy, which is the one responsible for the tsunami warning in Mexico, of a potentially impending tsunami. And we have not had too many earthquakes since we have had the network operating, just that one at the very beginning. But of course, Chile and my good friend Sergio Barrientos always comes with help because they have more than enough. And we tried some of the large Chilean earthquakes in the last 15 years or so. And this is the one in Illapel. And if you see the box on the right, it has what we obtained in terms of the magnitude, the length of the fault, and the width of the fault based on the inversion method. And we did quite well. We did quite well using this very high quality data from the Chilean networks. And we did it for Tohoku, and we did it for Maule and some others. And the results are relatively good. Tohoku not so much because of what you well know, the location of the stations on the coast and the rupture being very offshore. But we showed that it can work. We showed our sponsors that it can work, even though we're lacking earthquakes. So to finalize, I let you let you read some of our conclusions, but I will simply say that our first two responsibilities to be able to monitor in real time the crustal deformation. We showed that we could do it, and we're just waiting for a larger event, and we trust that it will work. And the second thing is the longer term, and by longer term I mean daily averages, which what is usually done for slow earthquakes and things like that. We can actually use these to monitor at least this part of the subduction zone in an accurate manner. So thanks again, and I'm sorry if I went over a few minutes. Thank you.
Thank you very much. I know we're at the end of our session, and I think people are queuing up, but maybe a quick question. Has anybody got maybe a quick question for Gerardo? Nothing online? Oh, you've got. Yeah.
There's somebody back.
Somebody
there? Okay.
Gerardo, thank you very much for interesting presentation. I have noticed that over the presentation you have been interchangeably using the terminology displacement and deformation. So my understanding the GNS sensors are using measuring displacement. To get to the deformation, you need to kind of apply the relative between points. So it's done in the post-processing business, I guess, something like that? Oh.
No, I was using it perhaps wrongly in a similar manner. What we measure, of course, is the displacement of the coast. And in the particular case that I showed in real time, if we assume that in those few minutes that we observed, the coast was undeformed, and it was only the earthquake and the post-seismic deformation that took place, we can measure the deformation based on the observed displacement. But thanks, Yuri. As usual, you keep me straight.
Thank you. Thank you very much once again, and thank you to all the presenters.